Hey everyone, I'm a small lizard, and continuing from the previous video, we will actually be looking more on arrangements, specifically repeated items and arranging items in a circular arrangement. Alright, so let's start with a very simple recap. So we recall that when we want to arrange, let's say, three unique items, it is simply 3 factorial, right? Because we can take 3 for the first item, then we branch out to 2 items, and then we branch out to the last one. All right, so let me just illustrate that a bit more explicitly. So let's say we have A, and then this, and then this. All right, so 3 times 2 times 1, which is 3 factorial. Now, so this then gives us the general case where if there are n unique items, then there will be n factorial number of ways to arrange n unique items. So what about the case where we have, let's say, repeated items? For example, A, B, C. Now, how do we then find the number of ways to arrange these items? It's actually very simple. Firstly, we have 4 items, so let's start with 4 factorial. Thereafter, what you notice is that when we arrange things by 4 factorial, we are assuming that every item is unique and that the order actually matters. But now, we have 2 A's where the order of these 2 A's themselves do not matter. And because of that, by performing 4 factorial, we actually counted the order of the 2 A's where we should have just taken them out. So it's time for us to take them out. The order of the 2 A's that we included is 2 factorial, so we divide by 2 factorial. So the idea is that, let's say for example, we have AABC itself, we actually counted AABC twice because we have A1 and A2, A2 and A1. And because of that, we will then divide by 2 factorial. And this actually applies to, let's say, let's say now 3 A's, 5 items, so it will be 5 factorial divided by 3 factorial. The idea is that now the arrangement of A1, A2, A3 don't matter, so we need to divide by how we arrange them. So within here is 3 factorial, so we divide by 3 factorial. So 4 factorial divided by 2 factorial will give us 12, 5 factorial divided by 6 would give us 20, right? 5 factorial divided by 3 factorial is simply 4 times 5. Now, what happens if we have, let's say, more than one item that's repeated? Let's say we have A, B, B, C, D. All right, same thing, 6 items in total, so 6 factorial. Now, the order between A1 and A2 don't matter. The order between B1 and B2 doesn't matter. However, the order between A and B still matters. All right, so you shouldn't be dividing by 4 factorial. It should be dividing by 2 factorial individually. All right, so 6 factorial divided by 2 factorial divided by 2 factorial is basically 720 divided by 4, so 180. All right, of course, if let's say we have A, B, B, C, D, it will be 7 factorial divided by 2 factorial, 3 factorial, right? Because there are 3 A's and 2 B's. Individually, we need to take away or divide by their arrangement. So that is repeated items. And this actually carries over to circular arrangement. Why? Now, let's say we have, again, A, B, C. But instead of arranging them in a straight line as we are looking in factorial, we'll be arranging them in a circle. And what you notice is that, let's say we have A, B, C. You notice that if you were to put C, A, B, it's the same. Again, if we, let's say, have A over here, and B over here, C over here, it's the same. All these 3 are the same, right? Because it's basically rotating on the spot. And if the seats are not numbered, if the spots are the same, aren't numbered or labeled, then you notice that there's actually rotational symmetry. And because of that, you notice that wherever we put the first item in, so let's say if you put these 3 seats, it doesn't matter where we put the first element in. All right, and that's why you notice that we divide by 3, which so happens to be the number of seats only. All right, so for very simple, for circular arrangements, if we want to arrange n unique items, it will be n factorial divided by n, right? Because n factorial, because you have n unique items, divide by n because there are n seeds in total which have rotational symmetry, which is simply n minus 1 factorial. Alright, so let's say we have A, B, C, D, E. We want to arrange them in a circle. It is simply 4 factorial. 5 minus 1 whole thing factorial, so 5 minus 1 is 4, then factorial. So let's take a look at how we can apply these ideas in an example. So how many ways can a word chocolate be rearranged? So we want to rearrange the letters. Let's start by listing out the different letters. We have C, H, O, L, A, T, E. We have 2 C's, 1 H, 2 O, 1, 1, 1, 1. Total of 9 letters, 2 repeated C's and 2 repeated O's. So very simply, we have 9 letters. So start off with 9 factorial, 2 repeated C's, 2 repeated O. Simply, or rather not really simply, we have to take 9 factorial divide by 4, which I can't do it in my head, so let's pull out the scientific calculator. 90720. Alright, so that is part A. There are 90720 ways. Part B, a circular band. So that should give you a clue. That's going to be circular arrangement. Made of 1 red, 1 yellow, 1 green, 1 black, 1 white bead. So there are 5 beads in total, 5 unique ways. So 5 factorial divide by 5, which is simply 4 factorial ways for the band to be made. So there are 24 ways. C, circular band is now made of 1 red, 2 yellow, 1 green, 3 black, and 1 white bead. So now there's a repetition, and we're going to put it in a circular band. Right? So very simple. Alright, it's the same way as we're going to do it for arranging items in a row. We're going to arrange the items in the circle first. So we have 1, 2, 3, 8 beads in total. So arranged in a circle, it will be 7 factorial first. Thereafter, we then consider the repetition. So 7 factorial repetition, 2 factorial, 3 factorial equals to, well, 7 times, I'm not going to do that live, so 6 factorial, so we have 420 ways. Alright, so that is the idea behind repeated items, arranging items circular, and me giving us a combination of circular and repeated items. Alright, so this is it. It's actually a very simple idea, I hope, and I'll see you guys in the next video.